Hello and good afternoon, everyone, and thank you for joining. So today I'll be presenting the outcomes of my MSc project over the past year and a bit. So this project is functioning under the Deciphering Developmental Disorders in Africa study, currently ongoing at the University of the Witwatersrand here in South Africa, where I am based, as well as at the University of Kinshasa in the DRC. And my supervisors for this project were Professor Lombard and Dr. Lamola. So developmental disorders occur due to abnormal and or delayed mental or physical development. And though there are multiple causes for DD, it is thought that 25 to 50% of developmental disorders have a genetic etiology. Yet the majority of our patients remain undiagnosed. The current gold standard for diagnosing the genetic cause of DD is chromosomal microarray. However, locally, or at the beginning of this project, microarray was not routinely offered as a diagnostic test for state patients here in South Africa. So instead, we perform cytogenetic karyotyping and MLPA as first-line testing, followed by FISH and single gene tests upon clinical indication. However, whole exome sequencing has emerged as the recommended first-line genetic test for the diagnosis of patients with DD, as this genetic technology has shown to have a higher diagnostic rate than regular testing procedures, allowing for better detection of the causal variants of these heterogeneous disorders. The utility of this test, however, has not been investigated in a limited resource setting, such as ours, but the acquisition of an Ion Torrent S5 semiconductor sequencer within our division made it possible to analyze the feasibility, diagnostic rates, and clinical utility of such a test in identifying pathogenic mutations in South African DD patients. The aim of this project was thus to implement a whole exome sequencing workflow on the platform and evaluate the financial and computational costs involved in the technique. Ethical clearance was received from the WITS Human Research Ethical Committee, and we then performed whole exome sequencing on 7 DD patient samples and 1 sequencing control. Data analysis was then performed across 3 investigative platforms that were later compared. We performed Sanger sequencing for variant validation and to determine the mode of inheritance of prioritized variants, and lastly performed a cost and diagnostic yield analysis. So in this project, we identified possible putative disease-causing mutations in 6 of the 7 patients, and were able to validate the variants in 5 of the patients. This investigation identified a patient with Takanushi-Kozaki syndrome, which to our knowledge is the first reported case in Africa, and this was seen in patient 1 in the CDC42 mutation. We also identified 2 cases of mandibular facial dysostosis with microcephaly in patients 3 and 7 in the ETAD2 gene, followed by congenital muscular dystrophy and mental retardation type B2 in patients 4 and 5, who are fraternal twins carrying the same compound heterozygous mutation. This is the comparison of the 3 data analysis tools or pipelines that we used. We ranked them based on their performance, with Moon coming in first, followed closely by the custom pipeline, which included a VEP annotation script with a DDG2P plugin. So this plugin was developed by the people over at the Wellcome Sanger Institute and Emble EBI, and the program was put together by myself and Mr. Aaron over at the Sydney Brenner Institute. And lastly, we had the VARAP software, which was unfortunately not very beneficial in our case. So these were the 4 categories that were the main defining features for the ranking, namely the number of variants prioritized per patient, the time for prioritization, the costing, and the number of patients in which we identified possible causative variants. Using the NHLS costing model, we determined the total comprehensive costing for this test to range at about 13,000 Rand per person or per patient, which was highly comparable to both the local and the international costing we investigated. So here you can see the research exome prices represent local costing, as diagnostic exomes are not currently performed in South Africa, and then the diagnostic exomes represent the international prices. So through this project, we achieved and refined a whole exome sequencing workflow for the investigation of DD in South African patients. We obtained a diagnostic rate of 70%, which is much higher than the global diagnostic rate of 40%. However, our samples were enriched with well-defined clinical phenotypes, which better led our investigation. And should the test be implemented in the local setting, we would then expect the diagnostic rate to drop to match the global statistic. We concluded that whole exome sequencing would be a highly beneficial tool in the investigation of DD within our department, and the feasibility of local implementation would allow steps towards personalized precision medicine in South Africa, job creation, and local skill development. I'd just like to acknowledge my supervisors, as well as Mr. Aaron over at the Simi Brenner and the Thermo Fisher technicians for their NGS training. Lastly, a thank you to our funders, our partners, and our collaborating institutions, as well as the audience for listening to my presentation today. Thank you.
Thank you, Kaitlyn, for an excellent presentation. I see we have a question from Natasha. So she says, I love the in-depth cost analysis. Well done. How do you think this cost will differ in other Southern African countries with fewer resources?
Yeah, great question. It was actually one of the limitations that we did identify through this project. The costing was quite tricky, especially in light with our current COVID situations. The import costs are dramatic. So unfortunately, the currencies do actually pay quite a big toll on the total costing. So I can't really say, but right now I think our costing just in the past 2 months, based off what I've done, has already gone up at about 3 to 4 grand per patient. So there are unfortunately quite a few considerations that may further impact the costing, especially further in Africa, yeah.
Thank you. And then we have a question from George, who asks, which software was easier to use, Moon or your custom pipeline?
Thanks, George. It was definitely Moon. Moon is very simple. You just upload your VCF file and you tap in your phenotypes and you click analyze and it does everything for you. It's completely automated. It's an artificial intelligence software, which is definitely very easy to use. Whereas the custom pipeline, there was some server interactions with coding and Linux and those kind of things. So for the layperson, I would definitely suggest the Moon was better.
Great, thank you. And then we have another question. Why particularly the Ion Torrent sequencing platform?
Yeah, so obviously Illumina is a lot more popular. So the reason we went for Ion Torrent specifically was, I think, basically for the on-site support. As Thermo Fisher, we do have technicians in South Africa, as opposed to Illumina. As far as I'm aware, we don't really have that much on-site support. And to be quite honest, it's honestly just the machine that we had in our facility at the time. So that was the main reason, yeah.
Thank you. And then I have one more question. And now that you've evaluated whole exome sequencing for this purpose, are there any plans for the department to use it or offer it to the public?
So we are definitely looking at it. We haven't started the implementation for developmental disorders specifically, but we have started with other panels for different disorders. We do just have to start implementing downstream analysis, like we need to set up servers for storage and those kind of things, probably get some bioinformaticians on site before we roll it out diagnostically. So things are in the works or motioning towards there, but not quite yet.
That's great news. Thank you. If there's no more questions, then we can move on to our next presenter. Thank you, Kaitlyn.